we are going to study now the functions that never decrease or never increase in a given segment. So let's define monotonic functions. Let's say we have a real function f that is defined. Let's say it's defined on an interval a, b. Okay. And then we say that it's monotonically increasing on the interval if any order we have between some numbers x and y, let's say x less than y, and both of them in the domain AB. Okay, that order transfers to the function. So that implies x less than y implies fx less or equal than fy. Okay, we are saying monotonically increasing, but we actually mean non-decreasing. Okay, you see that the possibility that f of x and f of y are equal is still there. Okay. Now, the definition for monotonically decreasing is similar. In this case, instead of going up, the function does not go up. Okay, it could stay the same or go down. So obviously, the easiest example would be f of x equal x. This is monotonically increasing. That doesn't seem correct. Monotonically increasing. Okay. You see, if obviously if x less than y, then f of x less than f of y. And we have f of x equal negative x. This one is decreasing. Okay, but we can have also a function that is defined as a graph. Let's say between -1 and 1. It could be something like this. Okay. So you see that here there are pieces where the function is not growing, but it doesn't go down either. Okay, so that those parts we always have the equality. Okay, so this one would be monotonically increasing, and then we can have something like this if we wish. This would be monotonically decreasing, again, even if it has flat parts. Okay, so sometimes we will just refer to monotone functions. Okay, monotonic functions. In that case, we are not distinguishing increasing or decreasing. It could be either of those. Okay, so if we say just monotonic functions, here is either increasing or decreasing. It cannot be both at once, okay? Unless it's a constant. The constant is the only function that is both monotonically increasing and decreasing, okay? Because it's always equal. Sometimes we will see instead of monotonic, we will see it written as monotone. That's also the same thing. And depending on the books, they will make a distinction between increasing or decreasing, and non-increasing, non-decreasing. Now I just realized I should have written here decreasing, okay, because decreasing corresponds to bigger or equal. But as I was saying, sometimes we will see, instead of what we wrote here increasing, we will see written non-decreasing, and here non-increasing. But that depends on the book. Okay, so monotone or monotonic functions are special in the sense that they are nicer than normal continuous functions. So let's say that f is monotonically increasing. And let's say, yeah, that's a hypothesis. The function is monotonically increasing, then the lateral limits fx plus, which is the limit as t tends to x from the right, f of t, and this is the limit from the right and the limit from the left, both exist. So the limit as t tends to x from the left, f of t, both exist. Okay, remember, this is not something that is obvious. For some functions, these limits may or may not exist. Okay. On this, when I say both exist, what I mean is both exist for every x in the domain. Okay, so you pick any point in the domain x, these lateral limits are going to exist. If you want, we can make it more precise. We can write it like this. We can say that the limit from the left is lesser or equal than f of x, lesser or equal than the limit from the right. Okay, and here something interesting happens. We can characterize these limits as a supremum and an infimum. So the limit from the right is the infimum of f of t for all the t's that are bigger than x. Okay, so let's say we have some increasing function here, and we have our x, and then we see clearly here when we approach x from the right that the lateral limit is the infimum. Okay, it's the infimum of all f of t with t bigger than x. Okay, you see? So this would be t1, t2, and so on. And the same for the left lateral limit. So in this case, it's the supremum of all the t's that are bigger than a but smaller than x. So in that case, we would be approaching t1, t2, and so on, and we would just keep going up. Okay, and we will be approaching f of x. Here what I drew is continuous, okay, but we can have also something that is discontinuous. For example, the simplest case would be a function that is, let's say, it's 1 and then it has a jump, and then it becomes 2. Okay, in this case, we see that the lateral limits are different, okay? Depending if we approach from the left or the right, okay? So that's something to keep in mind. That's the reason why there is a less or equal here instead of an equality, okay? If the function is continuous, then these are both equalities. If not, anything can happen, okay? It could be that the value of the function at the point is up, or maybe it's down, or it could be somewhere in the middle. Okay, we can define it in multiple ways. Okay. There's one more thing that I want to add to this theorem. That is that, oops, here. Yeah. So if we have some x less than y, then f of x plus less or equal than f of y minus. This actually, when we write it, it looks more difficult than it is. Here we are saying that if we have x number that is smaller than some other number y, okay, the right limit for x is less or equal than the left limit for y. Again, even if we have a discontinuity, there we go. So let's say this is x and this is y. So here what we are saying is that the right limit for x, this would be f of x plus, is less or equal than the left one for y. Okay, just because they are x and y are in order, x is strictly less than y. Okay, so let's see. There are several things here that we need to prove. The first one is that both limits exist. Okay, the second one is this identity here, this chain of inequalities. Actually, this characterization here as the infimum or the supremum is what we need to show. And then the last thing we want to show is that we have this inequality f of x plus less or equal than f of y minus whenever x less than y. Okay, and this I did, I mean, this is obvious, but let me just mention. This I wrote it for, let's use a different color, for increasing functions, but for decreasing functions, there are corresponding results. Okay, the only thing that would change are the inequalities. Okay, so let's get ready for the proof. Let's keep this over here. So proof. There we go. For this proof, the first thing we are going to be doing is to look at the set. Let's call it E, for example. The set of numbers f of t such that t is in between a and x. Okay, remember here when we look at the here, we are going to work on this inequality. So here we want to approach x from the left. So we are going to be looking at all the points t that are in the domain. That means that they are bigger than a, but they are on the left of x. So they need to be less than x. So once we define this set E, then E is bounded above because f is increasing. And in fact, it's bounded above by what number? By f of x. Okay, because that's the largest it can get. It's monotonically increasing, so it will be largest the more we move towards the right. So if we want, we can write this f increasing implies, there we go, implies that E is bounded above by f of x. And if we have learned something about the supremum and the least upper bound, is that if E is bounded above by f of x, then there is a least upper bound A. Now, A must be less or equal than f of x. Okay, it cannot be larger because of the way we have constructed E. Okay, every point in E is f of t for some t that is on the left of x. So the largest it can get is f of x. Now what we want to show is that a equals the limit from the left at x of the function f. Okay, this is what we want to show. So it's important to keep in mind. Maybe no need to underline it so that we don't get confused. Just a reminder, what does it mean that a equals the left lateral limit? So this is the limit of f of t, t tends to x from the left. Okay, so as a reminder, this means that well, let's write the whole thing. A equals f of x minus if, okay, f of tn converges to a as n goes to infinity for all, okay, for all sequences tn such that for all sequences tn in ax, meaning on the left of x, such that tn converges to x. Okay, so this is the actual definition. So we need to connect this to what we want to show, that a equals f of x minus. Now, because it's a proof with limits, let epsilon bigger than 0 be given, okay, any epsilon. And then from the definition of A as a list of upper bounds, then we find that there exists, let me write the full thing, there exists some t, okay, in AX. Why do I say that? Because in the set E, all the t's are in between A and X. Okay, so there exists t in AX such that f of t is in between A minus epsilon and A. Okay, why is that? Because this one here is obvious because we are working in E. Okay, this is A is a bound for E. Okay, actually less or equal, and then A minus epsilon is smaller because it cannot be A minus epsilon cannot be an upper bound. If it were, then we would be violating the definition of E. Okay, but then we can write T as X minus delta for some delta small enough so that actually A is smaller than X minus delta, smaller than X. This one here is obvious, okay, because of course. This one here, we need that X is not too large. Okay, we know already that A less than X. Okay, so there is some space. So as long as we take some delta that is smaller than this distance X minus A, then we're fine. Okay, so that's what I mean, delta is small enough. Okay, so once we have it set up like this, that A less than X minus delta less than X, then A minus epsilon less than f of X minus delta less or equal than A. This is what we need. Okay, we have this inequality. But then we also have, because f is monotonic, okay, we have another inequality that says that because X minus delta is less than t less than X, okay, we have that f of X minus delta is less than f of t less than f of X. And of course, this is less or equal than A. So let's keep these two in mind. And from here, what do we have? So we can put together A minus epsilon less than f X minus delta less than f of t. Okay, that's, let's say, the first, let's call it like this one. And then the second part that I want is that f of t is less than f of x, which is, well, actually I can just shorten it, less or equal than a, which is strictly less than a plus epsilon. So these two together are saying that a minus epsilon less than f of t less than a plus epsilon, which is the definition of f of t minus a less than epsilon. And this is what we wanted, okay? Because once we have this, notice what we have proved. X minus delta less than t less than x implies f of t minus a less than epsilon. Okay, so this is the definition of the limit from the left being equal to a. Okay, for every epsilon, we saw there exists delta, and so on. So this proves the first part of the theorem. Now, notice what we have proved. Let's go back to the statement. So we have proved this one over here. We have proved that they exist, and we have proved this one. Okay. So what we need to prove now is this number 3. Just one quick comment. So we have proved actually this one too. Okay, to prove this part of the inequality number 2, we would repeat the argument we have done, but instead of the supremum, we would take the infimum. Okay, but the argument is exactly the same. So let's focus on number 3. Now for this one, we just take x and y as in the statement. Okay, two numbers, x less than y, that are in the domain AB. And then we are going to apply the identity we just, the inequalities we just proved. So let me copy paste. Copy. Okay. So here what we are going to do, we just take this piece over here and this piece over here. And we are going to apply it, one to x, the other one to y. Okay, so let's apply f of x plus, because that's what we want. Okay, remember, we want to show that f of x plus is less than f of y minus. Okay, so those are the two we want to work with. Now, for the second, of course, instead of x, I'm going to write y. And here, we would like to get these two in order. Okay, this is an infimum, so it should be less than the supremum, but there is a problem because there is a bit of a mismatch here, you see? There is an x in one, the other one has a y. So no, that's not going to work. But we can adapt. Okay, because see what happens. So we have our function f here. And we are taking, so this is x, this is b, this is y. Okay, and we are taking the infimum. In the first one, we are taking the infimum of f of t for all the t's that are bigger than x. Okay, so we are approaching here. You see that we are allowing t to go all the way up to b. But you will agree with me that actually the t's that are in here don't matter at all. We could say that they don't count for the infimum. Okay, so you're doing a final countdown. You could count down from 10 or from 10 billion, but doesn't get interesting until the 3, 2, 1 go, right? So it's the same thing. So what I'm saying here is that the infimum, okay, this infimum over here, I might as well write it as the infimum of f of t when t is on the right of x, but instead of less than b, just less than y. Okay, I'm throwing off a few values, but it doesn't matter. Those are not going to affect the infimum, because for the infimum, what matters is like a limit, okay? And then similar for the supremum, okay? Here the supremum, well, I would need a different picture, but here the idea is the same. Okay, this is the supremum of f of t, but because I want larger, okay, I don't really need to go from all the way from a. I could just say, well, t less than y, I want to approach y, and for that I might as well just take x, okay? Let me actually go ahead and do the picture. So this is x, this is y, and here we have some a, okay, and we want the limit, the supremum, as we approach y. Okay, this one over here. What I was saying, we can have like lots of values, but the ones that matter are the ones that get really, really close to y. Okay, and those are past x for sure, because there is a gap here. Okay, so, but now, look at these two. The infimum and the supremum are both taken over the same set. So then, clearly, f of y minus, because it's a supremum, let's write it the other way around. F of x plus, because it's an infimum, is less than f of y minus. Okay, and I could actually say less or equal. And this completes the proof of the theorem. Now, an important consequence, corollary, is that monotonic functions do not have discontinuities of the second kind. Discontinuities of the second kind. And this is actually very straightforward, because we just proved that the lateral limits both exist. Okay, and that's the only condition for the first kind. Remember, a discontinuity of the first kind if the lateral limits existed, second kind otherwise. So as long as they exist, it cannot be of the second kind. Now, with this corollary, we will be able to show that every monotonic function is discontinuous at a countable set of points at most. Okay, no matter how bad, it will have at most a countable number of discontinuities, but we will prove that in the next video.